Swayam Prabha. Digital India. Educated India.
Once again, welcome you to this lecture, soil mechanics or geotechnical engineering 1, and I have completed my lecture on permeability and seepage, and there I have taken one session for showing the application of various method or various formula we have derived, and but partly I could not take it, particularly on critical hydraulic gradient, which again will come again when I will discuss effective stress and all, but immediately I will try to take one or two application for showing the application of critical hydraulic gradient, and also I have just completed the compaction. And compaction basically lot of information we have to keep in mind, but simultaneously there are some small calculation, and particularly to find out the optimum moisture content, dry density in the laboratory and all, some calculations will be there. So I'll with this my lecture actually with this session I'll take two problems from critical hydraulic gradient, that is permeability and seepage aspect, and two problems from compaction, and then I will just show the application. So first problem will be, this is a problem actually, first problem, a large size excavation is made in steep clay whose saturated unit weight is 17.27 kilonewton per meter cube. When the depth of excavation reaches 7.5 meter, cracks appear and water begins to flow upward to bring up sand to the surface. Subsequent boring indicate that the clay is underlain by sand at a depth of 11 meter below the original ground surface. What is the depth to the water table outside the excavation below the original ground level? So this is the one. So initially excavation is going on, and there is no water visible, it is saturated, or saturated or partly saturated, but at certain, when it reaches to a certain depth, the bottom cracks appeared and sand boiling type of effect started. So that means there is some pressure from bottom. That's what actually, that is the concept of critical hydraulic gradient. I just show this application, and you can see that typically I can show you this is the one. Suppose this much excavation is done and where actually cracks form, and subsequent investigation found that there is a sand layer at a depth of 11 meter. So this is 11 meter and this is sand, and this is actually 7.5, and then this will be your 3.5. So what happens, there may be, because of some source water is there and it is giving some hydrostatic pressure here. So if I put a piezometer here, somewhere here, and it will represent the how much pressure is acting here. So that height maybe we can if I insert a piezometer here, that water will rise up to that level. Since it is a clay layer, permeability is very low, you will not see the water, but when you punch this layer and make a piezometer, then you will see the water level. Suppose this is the water level H, then what will happen, I have to consider the equilibrium at this point. That means whatever weight downward weight is coming and whatever upward force because of this water is going, this when they are equal, that is the problem critical point, and that point actually cracks develops. If it is if you go further, then complete bursting will be there. So that simple calculation will be, since the unit weight of the soil is given 17.27 and multiplied by the depth is only 3.5 and equal to H into gamma W. Since I am not taking any factor of safety, at that depth only it is cracked upper, so I consider just this is a just verge of instability. Okay, so that condition, so this and this must be equal, or this is become just slightly greater because of this has happened. So this is the limiting height. That means at this condition, if I put a piezometer, what height you will see the water. So that will give you from this calculation. So it gives you H equal to 17.27 into 3.5 divided by H 9.81 gamma W. So this gives you 6.16 meter. So this is a very simple application. Sometime this soil instead of I have taken as it is, sometimes it may give the whether it is saturated, partially saturated, then accordingly you have to calculate unit weight and all. There can be some type of problem, but this is another very simple problem, just considering the equilibrium at this point. Now I will go to second problem. This is a second problem is if excavation is carried out in a soil with porosity of 0.4 and the specific gravity of solid of 2.65, determine the critical gradient. So this is the thing I have given. I have derived a expression, the critical hydraulic gradient equal to Gs minus 1 by 1 plus E. So that will come straightforward, but here E is not given, this porosity is given, and again we know the relationship between porosity and void ratio, that we will utilize. The next part is a 1.5 meter layer of the soil is subjected to a upward seepage head of 1.95 meter. What depth of coarse sand would be required above the soil to provide a factor of safety of 2.5? Assume that sand has the same porosity and specific gravity of solid as the soil. So when you are do the equilibrium, then you need to find out the unit weight. So void ratio etc. is required. So sand also whatever will be used, that porosity is it is given, that can be assumed the same. So if you do that, then how will proceed? We can see this way. You can see E equal to n divided by 1 minus n, and this is 0.4 divided by 1 minus 0.4, that is 0.4 by 0.6 equal to 2 by 3, and which is nothing but 0.67. So E value is obtained now. Once you get the E value and GS value is given 2.65, then IC will be equal to GS minus 1 by 1 plus E, and if you put all those values, that will 2.65 minus 1 divided by 1 plus 0.67, so it will be 1.65 by 1.67. So that gives you 0.988. Now another situation is given that there is a 1.5 meter of sand and some water is given from allowed to pass suppose this way, and with a head of suppose head applied is 1.95, it's shown here 1.95, and this is only 1.5. Okay, so that is the requirement is how much sand to be put here, because since this is height is more, the critical hydraulic gradient will be something, and it may because of this height when you allow flow from this, then the sand may wash away. So, because of that you have to put additional weight to balance it, and that too you have to provide factor of safety 2.5. So, that consideration if you take, then you can see we can consider. So, clay to be used. So, since flow is passing through this, there is no water table, but since water is passing through this, I can consider gamma saturated for the soil, that is actually Gs minus Gs plus E by 1 plus E into gamma W. So, if I put 2.65 plus 0.67 divided by 1 plus 0.67 into 9.81, this gives you a unit weight of 19.5. And sand, suppose the same property can be used, but you are putting above, you can assume that sand is dry. Suppose gamma D is Gs gamma W by 1 plus E. So, you can say 2.65 into 9.81 divided by 1 plus 0.67. This gives you a unit weight of 15.56. Now, we have to how much weight is coming, then I suppose take this is height h now. So, h into 15.56, that is weight is there, plus gamma saturated 19.5 into how much 1.5, and how much water pressure is there, this is the 1.95 into gamma W is 9.81. So, this is actually disturbing, that means causing the flow of sand along with water, and this is the resisting. So, resisting by this supposed to be factor of safety, which is 2.5. If I do this, then by simplifying this one, I can find out H equal to approximately 2.5 meters. Or whatever, maybe it can be calculated and checked, it may be 2.5 meter. So, that means around that much of soil, if you put here dry sand, and even if I apply 1.95 of head upward head to flow water through this soil, still you will have a factor of safety 2.5 against critical hydraulic gradient. Means what, actually at that point, since I have not discussed the shear strength yet, so I am not able to use that. Actually at critical hydraulic gradient point, actually the soil loses shear strength, actually it become less, and because of that, if you put any load on it, then it will not be able to support it. So, it will be like a flowing condition. So, that I will discuss again later on. So, this is another application, second application, that is to achieve a particular factor of safety, you can do something. So, that is the application I have shown here. So, third application, it is on compaction, and it is a very straightforward application, and you can see that the following data refers to a light compaction test as per Indian standard, and this is the, as I have told you, that compaction test is done in the laboratory, which is having a standard mold of 1000 cc volume, and standard proctor test if you consider, then there will be hammer weight of 2.5 kg and height is 30 centimeter. That means on 30 centimeter height, the hammer will be dropped on the soil, and this 1000 cc volume will be compacted in 3 layers. So, 1/3 first filled up, give 25 blows, then second 1/3, then again 25 blows, third 1/3, again 25 blows. So, like that you have to compact the soil in a mold of 1000 cc, and then you have to find out the weight. If you know the weight, and by finding out the know the volume, then you can find out the bulk unit weight. Then after knowing the water content, you can find out the dry unit weight. So, water content corresponding to dry unit weight get from the compact. So, I have mentioned that we generally do 5 trials, 2 to 3 will be dry side and 2 to 3 will be wet side. That means optimum is there. either exactly we may not get the point at the optimum, 1.1 optimum, maybe 2, 3 will be before optimum and 2, 3 before after optimum, and from there we will get the trend, get the curve. So that is what it is given here. 5 tests given, water content and corresponding weight sample, that means for a volume of 1000 cc, 8.5 and 1.8 kgs. When it is 12.2%, then it is 1.94, 13.75, it is 2, 15, like that 5. So now what we have to do, if the specific gravity of soil grains was 2.7, plot the compaction curve and obtain the maximum dry unit weight and the optimum moisture content. Then plot the 80% and 100% saturation line. If it is proposed to secure a relative compaction of 90% in the field, what is the range of water content that can be allowed, which I have shown that if you have a compaction curve, it has a dry density, but if I want to know 95% of that, suppose you have got 1, 95% of 1 means 0.95, then I will draw a line, horizontal line on 0.95. So 0.95 dry density will be both sides of optimum. So that range you will get. And would the 20% air void curve be the same as the 80% saturation? This is the point, this is the question asked. So now for this we need to do some calculation, and those calculations are like this. We have to prepare the we have to prepare the sample, and you can see this IS mold is the volume is 1000 cc, and generally your gamma D will be equal to gamma bulk divided by 1 plus W. So this is the one thing you can use, and so using this table you can see 8.5% of water content, then you can find out gamma D. First you can find out a gamma from the original weight by volume, we get bulk unit weight, then bulk divided by 1 plus 0.085 if you do, then you will get this one. That power 8.5%, this is the dry unit weight, 12.2 this is the dry unit weight, 13.7 this is the dry unit weight, 15.5 water content this is the dry unit weight, 18.2% this is the dry unit weight, 20.2% this is the dry weight. Now gamma D with so now if you plot this one, water content versus dry unit weight, then we will get a curve that I will come later on together. And now I have to find out gamma D for S equal to 80%, gamma D for S equal to 100%. So gamma D expression is like this. This is the gamma D, and gamma D will be equal to GS gamma W by 1 plus E, and E, S into E equal to W into G. So E can be substituted WG by S. So that is the thing we have done. Now in this 80% saturation means I will take S equal to 0.8, and water content is same, and GS is same, and everything is unchanged, and instead of E I am using now this expression, and there once I will use 0.8, another I will use 1. So when I use 0.8, these are the results for different water content, and when I use SR equal to 1 and what different content, these are the results. So moisture content versus dry density as it is in the lab with 100% saturation and 80% saturation, 3 data set we have got, and these will be plotted now. If I plot this, suppose this is a gamma D and this is moisture content. So, a typical curve will be something like this, and we may get a moisture content. So, this gamma D if you do, and you will get 17.45 if you plot in a particular curve 17.45, and this moisture content you have got optimum actually 15.2%. And now as I have mentioned that 95% of that, so 95% of that if you do 9 into 0.9 if I do, that gives you a value 16.58, and that 16.58 suppose this one, and if I draw a horizontal line, then you are getting two moisture content, this and this. So, this moisture content actually is 10, this is around 10 and this is around 17. So, that means your second part or third part, answer to third question actually 10 to 17% water you have to add to achieve that much, then 90% of density. And second part actually is given plot 80% and 100%. So, 100% saturation line will get something like this, whatever table previous table is there, water content versus dye unit weight, if you plot them you will get a curve like this, and 80% if you plot you will get a curve like this. Now, the next part is fourth part is mentioned whether 80% saturation line and 80% air void lines are same. So, I will take a gamma D equation in context of air content. That is the expression I have derived once, gamma W 1 minus Na divided by 1 plus W into G. Suppose I will take first set of data, that is 8.5% water, water content is 8.5% and Na equal to suppose 20%, 20% air voids. So, in that case if I put all those things in this expression, then you get gamma D equal to 17.2 kilonewton per meter cube, and whereas yes 80% from the table will get gamma D corresponding to 80% saturation, whatever you have calculated and shown in the table, from there actually you get gamma D equal to 20.56. So, 20% air content and 80% saturation, they are not correct, they are not same. That is what we want to mention here. You are getting gamma D by this is a 20.52 and other case you are getting 17.2. So, this is the answer to the last part, whether 80% saturation and 20% air content is the same or not. It is not same. But you can also check with some other water content, second set of water content, and there suppose it is 12.2 W and Na again 2.2. If you use this expression, you will get another dry density, and refer back to the table and find out corresponding to that water content 12.2% what is the dry density, and you will see that they are not the same. So, this is the one I wanted to point out here. And now, your last application. Last application is here at another problem. This type of problem once I have taken when I have done 3-phase diagram, similar to that, only little additional things are there. A 1200 meter long embankment of width 8 meter and 0.7 meter compacted thickness is to be constructed in a part of a roadway project. There is a big project, but out of part of a project is 1200 meter 1.2 kilometer long, and its width is 8 meter and height is 0.7 meter. Construction specification required the soil to be compacted to moisture content of 19.6%, achieving a dry unit weight of 17.0 kilonewton per meter cube. So, this is the requirement at the site. So, what are the things are known? Volume of the compacted work is known, and requirement, what is the dry density, what is the moisture content is known, and soil is to be excavated and transported to the site from a borrow pit where soil has moisture content of 15% and bulk unit weight of 17.2. So, there actually bulk unit is given, water content is given, then I can find out dry unit weight. From there actually I can again find out what is the volume required from the borrow pit to get that much volume of compacted volume. While loading into the dump truck, the soil loses and its dry unit weight drops to 14. So, when you excavate from the site, obviously soil will be loosened, more volume will be occupied in the truck. So, that is what during that time it is approximated given that 14 kilonewton per meter cube dry unit weight will get. So, if that is the condition given, for that you have to find out the volume of soil to be excavated from the borrow area, the number of trips of truck between the borrow area and the construction site, assuming each truck can carry 7.5 meter cube of loose soil. Then third, the volume of water in cubic meter to be added at the construction site to achieve the desired moisture content before compaction. See, site actually water is 15%, but actual construction site we require 19.6%. So you have to add water. So what is the amount of water that to be calculated? Degree of saturation of soil at the construction site after compaction, and the moisture content when it is during flooding, when it is saturated, what is the moisture content. So these are the various aspects we have to find out. Now I will take one by one. So volume of constructed site, volume of constructed site. So this will be 1200, that I suppose say VC, 1200 into 8 into 0.7, that will be that will be equal to 6720 meter cube, and gamma D is given 17.0 kilonewton per meter cube, that is actually equal to GS into gamma W by 1 plus E, and if I take GS equal to 2.7 and gamma W equal to 9.81, then and this is known, so this gives you E equal to 0.558, 0.55 sorry, yes. So this is the one. Then if I know this, then I can find out now VC will be equal to, what is the, in a VC actually compacted volume of soil, there will be solid and voids. So I can imagine Vs and Vv. So if I in that form, if I write Vs into 1 plus, suppose this is a constructed site, so EC. So this gives you Vs equal to, because EC can be substituted here, and VC is known, this one, this is equal to 6720, and from there we will get Vs will be equal to 4313. So Vs you have got. Now once you get the Vs, and then at borrow site, we have got gamma B equal to 17.25 and water content is 15%. So gamma D will be equal to 17.25 divided by 1 plus 0.15, that gives you 15.0, and so 15.0 can be written as GS gamma W again 1 plus E borrow pit. From here actually if I take again same GS, if I take same here, then this gives you EB will be equal to 0.766, 0.766, and once you got EB, then I can VB I can get, volume at borrow pit we can get, that is actually Vs 1 plus EB, and Vs should be same amount of solid should be transferred to soil. So it will be 4313 into 1 plus 0.7666. So that gives you VB equal to 7615 meter cube. So it will be definitely whatever the actual compacted volume, borrow material has to be more than that. So that is the thing we have got. And now during filling or excavating, your gamma D is 14, gamma D is 14, and that will be equal to, again I can do GS gamma W by 1 plus water content is given actually that one no, so 1 plus E suppose, and E it is not known, so it is E transportation time, what is the void ratio. So if I again this, if I take same as this, then this gives you E transport time will be a value 0.891. So, V transport will be how much? Vs into 1 plus E transport. So, if I use this value here and Vs already known, if I use, then I am getting a volume equal to 8150 meter cube, and each truck volume is 7.5. So, how many trip required? Trip number will be equal to 8150 divided by 7.5. This gives you 1088 trip. Now, third part I have to find out, that is first, second is over. Third part is, I know VW equal to WW by gamma W, and that can be written as W into Ws by gamma W. So, if I take now VW construction side, then it will be Wc into Ws by gamma W, and W at borrow, this will be equal to W borrow into Ws divided by gamma W. Then delta W, which is what are required, VWC minus VWB, and if I do this, then it will be Ws by gamma W into Wc minus Wb, and Ws nothing but gamma dc into Vc, Wdc into Vc divided by 9.81 is gamma W into Wc is 0.196 minus Wb is borrow side is 15%, 0.15. So, if I do this calculation, it gives you 535.6 meter cube. So, this is actually, that means how much water, that means borrow side, from the borrow side the amount of soil you are taking, in that soil you have to add this much meter cube of water to, and then compact, then only you will get the desired thing. So, I will get this continuation of this, that means two more parts, they are quite small, and fourth part was what is the degree of saturation at compacted site, and for degree of saturation we know the equation, that is S into E equal to W into G, and you know the water content, you know this 2.7, you know the E, then if that means you will get S equal to Wg by E. So, that gives you all values, if you put 0.196 into 2.7 divided by E is 0.558, it gives you 94.8%. And last question was, when it is flooded and that means entire soil will be saturated, then what is the water content? When it is flooded, that means soil will be saturated. So, saturated means S equal to 100%, and in that case same equation is valued, the S into E equal to W into G, and S equal to 1 and W equal to how much actually you have to find out. So, W equal to ultimately E by G. So, that means E is 0.558 divided by 2.7, this gives you 20.6%. So, actually construction site we had water content of 19.6, because of the flooding the water content will be slightly increased, so 20.6. So, that is the, so various application on both critical hydraulic gradient and the compaction. So, these are the type of compaction equation calculation you have to do during compaction. Of course, in advanced level, as I have mentioned, when you have to do dynamic compaction etc., you have to do some calculation for finding out the weight, height and the vibration level. So, that is of course I am not including, because it is generally not in the syllabus of undergraduate level. So, with this I will just conclude the compaction Maybe next lecture onwards I will take some new topics. Thank you.